Good morning, everyone. This is Yangyang Fu from University of Colorado Boulder. Today, I will talk about how to utilize data center to harvest the benefits from multiple electrical markets. This is my agenda. First, I will talk about the background and the motivation. Then, I will introduce a new synergistic frequency regulation control that enables data center to provide a fast demand response. And next, I will talk about a model-based optimal control framework that helps the data center to minimize its operational cost by participating in energy markets and regulation market at the same time. Um, all these controls will then be demonstrated in a numerical case study. And in the end, I will wrap up the presentation with some conclusions. So first, electrical markets. In a deregulatory region, RTO or ISO, usually known as the grid operator, run three types of markets. Electrical markets to uh, manage the balancing between the supply and the demand. These three markets, capacity markets, energy markets, and synergy service markets, focus on different time scale of operation. For example, uh, focus focus on the planning of generation. For example, at least 1 year ahead. Energy markets usually focused on the balancing day ahead or hourly ahead. The ancillary service markets usually focus on the short-term balancing, for example, within an hour, like minutes or seconds. Frequency regulation, as one type of ancillary service, requires a power balancing at an interval of seconds. Providing frequency regulation by buildings actually means the building should be able to continuously adjust its outputs, the power outputs, to track a reference signal received from power grid. So in data centers, to enable a data center to track a frequency regulation signal, we have to have a frequency regulation control. This section, we propose the synergistic FR control strategy for data centers. The schematic is shown in this slide. It consists of four parts. Baseline routine. In this baseline routine, we calculate the baseline power of the data center when it's not used to provide FR. And then we will use the baseline power to calculate the reference power signal that the data center should follow when providing FR. And we also have a server power management module and a cooling tower management module, which can regulate the server power and the cooling system power separately. So for the reference power signal, there are two functions in this module. The first is to determine the regulation capacity offer. The second is to calculate the reference power signal, as I show in these two equations. The delta P is the power range that the data center should operate within when providing frequency regulation based on the capacity bits C and the regulation signal R. The regulation capacity bits can be determined optimally using the optimal framework that I will talk about later. The delta P is then added to the baseline power to get the final reference power signal that the data center should follow at real time. The server power management considers a control for an aggregator of servers. In this module, we also have two functions. The first is to determine the number of active servers every hour based on the predicted workload. The second is to regulate the aggregator frequency every 4 seconds based on the FR signals from the electrical market. So for the first one, the number of active servers, we choose to modulate the number of active servers every hour because the servers are actually took a relatively long time to be activated or deactivated. This equation shows the number of active servers at each hour based on the predicted workload and the service rate that a server actually can operate at. The division of these two give us the number of active server. We introduced a flexibility factor that can help improve the frequency regulation performance in this equation as shown as beta here. The performance of beta will not be discussed in this presentation. If you're interested, you can refer to one of our previous published paper. The second function of server power management is to regulate the frequency at an interval of 4 seconds using a PID controller. The PID controller will output the frequency of the aggregator within the bound. The bound has a minimum value, frequency minimum frequency. It's determined by the response time required by the data center to provide normal calculation service or web visiting service. So it actually means the quantity of service has to be satisfied even during frequency regulation. The maximum frequency, we use the nominal frequency of the server, which is normalized as 1 in this case. The other power management module is a cooling power management module, where we continuously adjust the cooling system power by resetting the chill water supply temperature set point. This equation shows how we reset the set point based on the baseline supply temperature and the regulation range we predefined and the regulation signal. This strategy actually has been experimentally studied in many studies to show that this strategy is able to provide frequency regulation, but with not very good performance because it's relatively long. Took a relatively long time to respond to the fast signal. But in our case, because we have servers which is fast response resource, this slow responding resources will be compensated by the fast responding resource. So it's not an issue here. So previously we talked about the frequency regulation control, where we enable the data center to track a fast changing power signal. In this section, we're going to talk about a model-based optimal control framework that help to minimize the operational cost of the data center during the provision of frequency regulation and participating in the energy market. So before I go to the detailed formulation of the optimization problem, I want to introduce a fact. We know that when we're providing frequency regulation, the regulation signal over a long time is usually considered as energy neutral. But when we calculate the energy of the regulation signal in a short time, for example, 5 minutes, 10 minutes, or even 30 minutes, it's not always energy neutral. So, which means, for example, as shown in figure A, if we provide frequency regulation at the peak power, the extra demand possibly could be imposed on this FR baseline calculated in 5 minutes or 15 minutes. So this will introduce extra demand to the system when the utility calculates the electricity bits. And figure B actually shows the normalized extra demand of 30 minutes during July in 2018 in PJM. We can see that it's totally possible that if we calculate the demand in 30 minutes, providing F4 can definitely impose extra power demand to the baseline. So we have to keep in mind that the extra demand, sometimes if it's too large, it will give us an extra demand charge, which may compensate the benefits we receive from frequency regulation. So the objective of this control is trying to minimize the energy cost, demand cost, and the revenues from the regulation service. This control is constrained by three conditions. The first, the frequency regulation capacity bit. It's the design variable. It should be bounded within a minimum value and a maximum value. The minimum is 0 here. We can choose not bidding, not participating in the next hour. And the maximum is defined by users or can be calculated from model-based models. The second condition is the service response time. This is to guarantee that the server can provide sufficient quantity of service during F4. And the third term is the F4 performance score. The performance has to be high enough to be considered as a quantified resource in the regulation market. These two control we just mentioned above or evaluated in a case study. In this case study, we modeled the data center cooling and IT system in a Modelica-based environment. All the controls also modeled within the Modelica environment. This is the preliminary results of this simulation study. We simulated 2 days in January and July respectively. The solid line shows the baseline without providing F4, and the shadow around the baseline is the capacity bits that we calculated from the optimal control framework. We can see the F4 capacity bit actually varies at different hours. This is showing us that the capacity bits is a result of regulation signal, energy price, and regulation price. The capacity bit varies from 5 kilowatts to 223 kilowatts at a different time. The optimization framework can give us a economic saving as $23 and $123 over 2 days in January and July, respectively. The savings are mainly from providing frequency regulation service. So, to quickly wrap up this presentation, we have demonstrated a synergistic control strategy to enable data centers to provide F4 to the power grid. And we also have an optimal control framework that can help data center to minimize the operational cost from energy market and regulation market by avoiding extra demand charges. So basically that's all for me today. If you have any questions, please let me know. Thank you.